Okay, so get this right. You're playing a video game and you're climbing the ranks,
Yeah.
like bronze to silver,
Okay.
silver to gold, you know how it is.
Yeah.
Well, the paper we're diving into today, gradient equilibrium in online learning,
Okay.
actually connects to how those ranking systems work,
Wow.
like ELO, which is used in chess, or even in those competitive games.
That's pretty fascinating, isn't it? How this idea of gradient equilibrium can apply to so many things,
Right.
like ranking algorithms,
Yeah.
or maybe even making machine learning models fairer.
Less bias. Yeah, sign me up for that.
Definitely.
But hold on, maybe we should back up a sec.
Sure.
What even is gradient equilibrium? I mean, I don't think all our listeners are like machine learning experts or anything.
Good point.
Hmm.
At its heart, gradient equilibrium is really about how these online learning algorithms behave.
Okay.
These algorithms that learn from data streams, they're always adapting, updating their parameters, on the fly.
Like a river. The data's like water, always flowing, and the algorithm's got to navigate that flow like a boat.
That's a perfect way to think about it.
Really?
Yeah, imagine that boat's trying to find the lowest spot in this valley,
Okay.
but it can only see a little bit of the landscape at once, right? It has to use the information from the river, the data coming in,
Right.
to figure out which direction to go.
Oh, okay.
That's basically what online learning algorithms are doing.
I think I get it.
Yeah.
But where does this gradient equilibrium thing fit in?
So as our boat's navigating the valley,
Yeah.
it's always adjusting its position based on the new data that comes in.
Right. Makes sense.
And these adjustments are guided by something called the gradient,
Oh.
which basically tells the algorithm which way to move its parameters to get better.
Oh, so the gradient's kind of like a compass,
Yeah.
pointing the boat towards its goal.
Perfect analogy. So gradient equilibrium comes in when we look at the average of all those gradient updates over time. The authors are really interested in what happens when that average gradient gets close to zero.
So it's not just about finding that lowest point,
Right.
but also about making sure all those little adjustments, those nudges from the gradient, balance out in the end.
Exactly. What's cool is that this balancing out can actually tell us a lot about the algorithm itself.
Oh, really?
Yeah. Things like, are its predictions unbiased? Are its estimates reliable? Stuff like that.
So this is kind of big deal then.
It is.
But how'd this whole idea even come about?
To get that, we need some historical context. For ages in machine learning, especially online learning, the focus was all about minimizing regret.
Regret, like the algorithm feels bad about its choices.
No, not quite. Regret here is how we measure how much worse the algorithm is doing compared to the best it could have done.
So it's like looking back and going, if only I'd picked these parameters, I would have been so much better.
Exactly.
Got it. So minimizing regret was the big thing for a while.
It was. And it's still important, don't get me wrong.
Right.
But this paper, it shifts the focus away from just minimizing regret.
Okay.
And puts the spotlight on this gradient equilibrium idea.
It's like saying, hey, instead of dwelling on the past and our regrets, let's look at the bigger picture,
Yes.
the overall balance of our choices, those gradient updates,
Yeah.
and see what that tells us.
You got it. And it's really cool because it lets us analyze these algorithms in a new way, revealing things we might have missed before, like putting on a new pair of glasses and seeing the world differently.
I love that analogy. That's probably why this paper is so important, right?
Yeah.
It's bringing a whole new perspective to machine learning.
Precisely. It's not just about tweaking things a little, it's a whole paradigm shift.
Wow.
And it's already sparking a ton of new research.
Okay, so we've got this big idea of gradient equilibrium.
Yes.
We've seen how it connects to ranking systems and maybe making algorithms fairer.
Right.
And we even took a quick trip down memory lane in online learning to see where it all fits.
Yep.
But how about we get into some of the nitty-gritty now? Like, how does gradient equilibrium actually work?
Sure.
What's the math behind it?
One of the key things here is something called a restorative loss function.
Okay, unpack that for me. What is a restorative loss function, and how does it help with this whole balancing act?
Imagine you have this ball rolling around on a hilly surface, right?
Yeah.
The shape of that surface, that's determined by the loss function. Now, the ball wants to find the lowest point on that surface, just like our algorithm wants to find the best set of parameters.
The ball's rolling around trying to get to the bottom. Got it.
Now, a restorative loss function is like shaping that surface so it has this natural pulling back effect.
Okay.
So even if the ball starts rolling away from the lowest point,
Yeah.
the shape of the surface will kind of guide it back gently.
Oh, it's like those bumpers in a bowling alley.
Exactly. They keep the ball from going totally off track. That's basically what these restorative loss functions are doing for gradient equilibrium.
So it's not just about minimizing the loss,
Right.
but also about making sure the algorithm stays balanced as it learns.
Exactly. And what's really interesting is that this paper explores all sorts of ways to make this restorative property happen
Right.
depending on the loss function we're using.
Right, because there are tons of different loss functions, right?
Tons.
Yeah.
Squared loss, logistic loss, quantile loss.
The list goes on.
It does. And each one shapes that hilly landscape we were talking about in its own way. The paper goes into detail about how some common ones have these restorative properties, and it even talks about how we can sometimes tweak loss functions to make them more restorative if they're not already.
Okay, getting a little technical.
Okay.
But I'm with you. We've got these restorative loss functions shaping the landscape
Yes,
to keep the algorithm balanced.
exactly.
And the paper shows us how to do that depending on what kind of loss function we're dealing with.
You got it. And what's also fascinating is they show how this can be different depending on how many dimensions we're working with.
Dimensions, like going from a flat surface to something more 3D.
Yeah, like that. Think of our bowling alley again.
Okay,
In a simple one-dimensional case, it's like bumpers on just two sides.
okay.
But as we add more dimensions, more parameters to our model, it's like adding bumpers all around the alley, making it harder for the ball to stray too far.
Oh, I get it. So in higher dimensions, we need a stronger pulling back effect to keep things on track.
Exactly. The paper even shows this with figure 5a, I think it is.
Okay.
It shows how those parameters can kind of wander off in these higher dimensional spaces if the loss function isn't restorative enough.
Wow, we've gone from a simple bowling alley to multi-dimensional landscapes and parameters going rogue.
We have.
This is seriously complex stuff.
It is, and we're just scratching the surface here.
I believe it.
But don't worry, we'll keep breaking things down as we go along.
Good, because my brain is starting to hurt.
I bet.
But seriously, this is all super fascinating. Thanks for walking us through it.
No problem.
I think we need to take a quick pause here. Yeah.
Just to let our listeners digest all of this.
Makes sense.
We covered a lot, from instancing gradient equilibrium to those restorative loss functions.
Mm,
But when we come back, I'm really curious to hear about some real-world applications of this.
definitely.
We touched on making algorithms fairer and understanding ranking systems, but I'm sure there's a lot more.
Oh, yeah. We're just getting started. The fun really begins when we see how these kind of abstract ideas actually help us solve real problems.
Okay, I can't wait for that.
Me neither.
All right, welcome back, everyone. Ready to go even deeper on this gradient equilibrium thing.
You bet. And like you said before, it's time to see how this theory connects to the real world.
Right. I mean, the math and all is cool, but I'm always more interested in how it makes things better, you know?
Absolutely. That's what's so exciting about this paper. It doesn't just stop at theory.
Okay.
It actually shows how gradient equilibrium can help us tackle some really big challenges in machine learning.
Okay, so tell me more. What kind of applications are we talking about? Well, one of the most interesting ones is in online conformal prediction.
Conformal prediction. That sounds intense. What's that all about?
Imagine you're trying to predict something uncertain, like tomorrow's weather,
Okay.
or maybe the stock market.
Yeah, tricky stuff.
Conformal prediction, it's about giving you not just one prediction,
Right.
but a whole range of possible values and a confidence level, too.
So instead of saying tomorrow will be 25 degrees, you'd say there's a 90% chance it'll be between 23 and 27 degrees.
Exactly. And what's really neat is that the authors show how gradient equilibrium can help us get these coverage guarantees, even when the data is changing all the time.
Coverage guarantees, meaning our prediction range will actually contain the true value a certain percentage of the time.
Precisely. That's super powerful when things are always in flux, which is most real-world stuff.
Okay, conformal prediction, check. What else?
I'm guessing there's more gradient equilibrium can do.
Oh, definitely. The paper also looks at how it can help us understand and even improve those ranking systems we talked about.
Like ELO. Yeah, ELO, the ones used in chess and video games.
Wait, seriously? This can shed light on something like ELO scores.
It can. And get this, they show how when you look at it through the lens of gradient equilibrium, ELO can actually give unbiased win rate predictions even when you've got tricky situations.
Tricky situations, like players trying to cheat the system.
Yeah, exactly. Even if people are trying to mess with their scores, ELO, analyzed with gradient equilibrium, can still give us fair and accurate rankings.
Wow, so it's like saying, go ahead, try to game the system. We've got the math to see through it and keep things fair.
That's a great way to put it. And they actually show this using a real-world data set from the chatbot arena.
The chatbot arena. So they're using it to analyze how chatbots are ranked against each other.
Yep. Taking this theory and applying it to the internet, basically.
That's so cool.
And it works. Their results show that ELO scores, when seen through gradient equilibrium, do give those unbiased win rate predictions.
All right, I'm convinced. Gradient equilibrium is like a secret weapon. It handles changing data in conformal prediction. It sees through cheating in ranking systems. What can't it do?
Well, it's not magic, but it's pretty powerful. Another area where it's really useful is in dealing with bias in machine learning models.
Oh, yeah, that's a huge one. All those stories about algorithms making unfair decisions based on race or gender or whatever.
Exactly. This paper shows how gradient equilibrium, combined with techniques like regularization, can actually help us lessen that bias.
Regularization, those things we add to models to prevent overfitting.
That's right. And what's interesting is that they focus on lasso regularization, which encourages sparsity in the model's parameters.
Sparsity, meaning the model uses fewer features for its predictions.
Exactly. By pushing for sparsity, lasso regularization can help stop the model from relying too much on sensitive features that might lead to biased outcomes.
So it's like saying, hey, model, don't use those sensitive features as a shortcut. Find other fairer ways to make your predictions.
Exactly. And what's really cool is that they actually give a formula for the minimum amount of lasso regularization you need to achieve this debiasing effect.
So it's like a recipe for fairness.
Kinda. And they don't just stop at lasso, they also look at ridge regularization, another technique for preventing overfitting.
Right.
And how that, combined with gradient equilibrium, can achieve something called multi-accuracy.
Multi-accuracy. Okay, another new term. What's that one about?
Multi-accuracy is about making sure our model is accurate, not just overall, but also across different groups in our data.
Oh, so it's not just getting the average right,
no,
but making sure we're not consistently messing up for certain groups of people.
Exactly. And they show that using either lasso or ridge regularization, along with the insights from gradient equilibrium, we can potentially get these multi-accuracy guarantees. It's like building safeguards to make sure our models are fair across the board.
This is seriously mind-blowing. Conformal prediction, ranking systems, bias mitigation, now multi-accuracy. Gradient equilibrium is like the Swiss Army knife of machine learning.
It really is a versatile concept, and it's not just about those specific applications. The real power is in how it gives us this new perspective on how we analyze and understand online learning algorithms overall.
So it's a whole new way to look at the field of online learning.
Exactly. That's why this paper is so important. It's not just a small step forward, it's a potential game changer.
Wow.
And it's already inspiring a ton of new research.
This is so much to take in. But before we get lost in the theory, I'm curious, what are the real-world implications of all this?
That's a great question.
Like, if I'm working on a real problem, how can I actually use these gradient equilibrium insights to make my models better?
Well, the paper gives some concrete examples.
Okay, let's hear.
One really cool one is in ensemble learning.
Ensemble learning, where you combine multiple models to make a prediction, like a team of experts putting their heads together.
Exactly. And the challenge there is figuring out how much each model should contribute.
Right, because some models might be better than others.
Exactly. What the authors show is that we can use this technique called online mirror descent to learn those weights in an online way.
Okay.
And guess what? Gradient equilibrium is key to making sure this whole thing runs smoothly.
So it's like having a team of experts that's constantly learning and adapting.
Yeah, a self-adjusting team. They show how this can lead to faster coverage in quantile prediction, meaning those prediction intervals become reliable more quickly.
Okay.
And also lower quantile loss compared to just using one learning rate.
So it's like getting the best of both worlds.
It is. And this idea of multiple learners connects to another application they discuss, debiasing predictions from those black box models.
Wow, black box models, the ones where we don't really know how they work inside. Debiasing those is so important.
Absolutely. And the authors show this neat technique for doing it online using the insights from gradient equilibrium. They show how you can continuously adjust your predictions to fix any biases that are sneaking in.
So it's like a little bias correction unit running alongside the model, always nudging things in the right direction.
That's a great way to think about it. And they even give you the code for these algorithms so others can try them out.
That's awesome. Giving us the tools to build fair algorithms.
They are. And what's really cool is they don't just stop at theory.
Right.
They actually test these algorithms on real data and show they work.
Because that's what matters, right? making a real difference.
Absolutely. And remember those ELO scores and ranking systems.
Yeah, how gradient equilibrium helps us understand them, even with players trying to cheat.
Well, they take it even further and use gradient equilibrium to analyze how those scores change over time.
Wait, what do you mean by change over time?
Imagine two players competing over and over.
Okay,
Their ELO scores will go up and down based on who wins.
right.
What the authors are looking at is how those scores evolve and if they eventually settle into some kind of balance.
Ah, so it's not just about the score at one point in time, but the big picture, how things change as players interact.
Exactly. And what they find is that under certain conditions, ELO does lead to a stable equilibrium. The scores eventually settle down into a ranking that accurately shows how skilled the players are relative to each other.
That's pretty cool. It's like saying, even though there are ups and downs, in the end, the best players rise to the top.
Exactly. And the stability is directly linked to those restorative loss functions we talked about.
Oh, yeah, those things that pull back and keep the parameters from going crazy.
Right, like the bumpers in the bowling alley, keeping the ball on track.
I remember.
Well, with ELO scores, those restorative forces are what help the scores settle into a stable ranking.
Wow, it's amazing how all these ideas connect in real-world applications.
It is. And this paper just scratches the surface. It opens up a whole new direction for research and online learning.
So as we wrap up this part of the deep dive, what's the big takeaway? What should our listeners remember about gradient equilibrium?
I think the key takeaway is that it's not just some abstract idea.
Okay.
It's a powerful tool for understanding, analyzing, and improving these online learning algorithms in tons of different areas.
Right.
Whether you want to make algorithms fairer, build more robust predictions, or just understand those ranking systems. Gradient equilibrium gives you a new perspective and a bunch of valuable insights.
Okay, we're back for the last part of our gradient equilibrium deep dive. We've covered a lot, but I'm ready to hear about those practical applications.
Awesome. You mentioned quantile tracking and debiasing black box models.
Right. Let's start with quantile tracking.
Yeah.
We talked about conformal prediction, but how does gradient equilibrium actually help us track quantiles?
Remember that example of predicting tomorrow's temperature range?
Yeah.
So instead of just one number, we want a range to show the uncertainty.
Yeah.
Quantile tracking is all about figuring out those boundaries,
Yeah.
like the 10th percentile and 90th percentile.
Okay.
That gives us a reliable prediction interval.
So it's like we're 90% sure tomorrow's temperature will be between these two values.
Exactly. And what's really cool is the authors show how gradient descent, that classic algorithm,
Yeah.
can be used to track these quantiles even when the data is changing over time.
Okay, I see. But gradient descent uses that learning rate, right? How do we know what learning rate to use for this?
That was a great question. And it turns out picking the right learning rate is tricky. Too small, and it learns too slowly. Too big, and it can go haywire.
So it's a bit of a balancing act.
It is. So the authors have this clever idea. Instead of one learning rate, why not learn a mix of quantile tracking iterates, each with its own rate?
Wait, so when it's like having a bunch of quantile trackers,
Yeah.
each learning in its own way,
Exactly.
and then we combine their predictions.
You got it. They show this can give us faster coverage.
Meaning?
The prediction intervals are good more quickly
Okay.
and lower quantile loss compared to just one learning rate.
That's pretty awesome, getting the best of all worlds.
It is. And this multiple learner idea connects to another cool application. They discuss debiasing predictions from black box models.
Ah, those black box models, the ones where we don't really get how they work inside. Debiasing those is a big deal.
Huge. And the authors show this really neat technique for doing it online using, you guessed it, gradient equilibrium.
You should have guessed.
They basically show how you can adjust your predictions on the fly to fix any biases sneaking in.
Oh, so it's like this little bias correction thing running alongside the model, always making sure those predictions are fair.
That's a great way to think about it. And they even give the code for these algorithms so people can actually try them out.
That's awesome, like giving us blueprints for building fairer algorithms.
They are. And what I like is they don't just focus on the theory.
Right.
They test these things on real data and show they actually work.
Yeah, that's what matters in the end, making a difference.
Absolutely. Speaking of making a difference, remember ELO scores and ranking systems.
Yeah, how gradient equilibrium Helps us understand them even when people are trying to cheat.
Well, they go even further.
Okay.
They use gradient equilibrium to analyze how those ELO scores change over time.
Wait, what do you mean change over time?
So think about two players competing over and over.
Okay.
Their scores will go up or down depending on who wins, right?
Makes sense.
What the authors look at is how those scores evolve.
Right.
And whether they eventually settle into some kind of balance.
Ah, so it's not just the score at one point in time, but the overall trend, how things play out as they compete.
Exactly. And what they found is that under certain conditions, ELO does lead to a stable equilibrium.
So that means...
The scores end up in a ranking that accurately shows the skill difference between the players.
Oh, cool. So it's like, even with ups and downs, the best players will come out on top in the long run.
Exactly. And this stability links back to those restorative loss functions we talked about.
Oh, yeah, the ones that pull back and keep the parameters in check.
Right, like the bumpers on the bowling alley, keeping things from going off the rails.
Yeah, I remember.
Well, with ELO scores, those restorative forces are what help the scores settle into that stable ranking.
Wow. It's amazing how all this stuff we've been talking about comes together in real applications.
It is. And this paper is just the beginning. It opens up so many possibilities for research in online learning.
So as we wrap up our deep dive, what's the big takeaway for our listeners? What's the one thing you want them to remember about gradient equilibrium?
I think the main thing to remember is that gradient equilibrium isn't just some abstract math thing. It's a powerful tool that can help us understand and improve online learning algorithms in so many different ways. Whether you're interested in fairness, robust predictions, or just how those ranking systems work, gradient equilibrium gives you a new perspective and a ton of valuable insights.
That's awesome. And who knows, maybe this paper will inspire some of our listeners to explore these ideas and come up with even more amazing applications.
I hope so. The future of online learning is bright, and gradient equilibrium is going to be a big part of it.
Thanks for joining us on this incredible deep dive into gradient equilibrium. We'll be back next time with another fascinating paper from the world of machine learning. Until then, keep learning, keep exploring, and keep those gradients balanced.